IBM just packed 100 billion transistors onto a chip the size of your fingernail. That's not a typo, 100 billion, and it doubles the density of the best chip IBM had announced just a few years ago. To put that in perspective, think about how small a transistor already is. The ones in your phone are just a few nanometers wide. A nanometer is roughly 100,000th the width of a human hair. IBM is now pushing below that threshold into territory that most engineers thought we'd never reach without completely rethinking how chips are built. And that's exactly what they did. For the past 60-odd years, chip progress has followed a rough pattern. Every couple of years, engineers managed to squeeze roughly twice as many transistors into the same space. More transistors meant more processing power, better efficiency, smaller devices. That trend is called Moore's Law, named after Intel co-founder Gordon Moore, who observed it back in 1965. The problem is that for the last decade or so, people have been saying Moore's Law is running out of road. Transistors are so small now that you're bumping up against the limits of physics. Atoms get in the way. Heat becomes unmanageable. The traditional tricks stop working. So IBM didn't just shrink things down the old way. They changed the architecture entirely. One of the biggest moves is what's called 3D stacking. Instead of laying transistors flat across a chip like houses in a suburb, you start building upward. Think skyscraper versus sprawl. When you stack layers of transistors vertically, you can fit far more into the same footprint without needing to make each individual transistor smaller. It's a fundamentally different way of using space, and it opens up a lot of headroom, but stacking creates its own headaches. The more you pile on top of each other, the harder it gets to move electricity efficiently between layers, and the harder it gets to pull heat out. IBM had to solve both of those problems at the same time. On the materials side, they moved away from some of the standard stuff that's been in chips for decades. At these scales, silicon alone doesn't behave the way you need it to. IBM used new semiconductor materials that carry electrical current more cleanly at tiny dimensions. They also refined the transistor design itself, using what's called a nanosheet structure. Instead of a traditional fin-shaped transistor, nanosheets are thin, flat ribbons of semiconductor material that wrap the electrical gate around them on all sides. That gives you much tighter control over the flow of current, which means less leakage, less wasted energy, and better performance. Less leakage matters more than it might sound. In a chip with 100 billion transistors, even a tiny bit of unwanted current in each one adds up to a massive power drain across the whole chip. Fixing that at the transistor level is one of the reasons this design can be more energy efficient, not just faster. Now, it's worth being clear about where this technology actually sits right now. This is a prototype. IBM's research division built this to demonstrate what's possible, not to ship it to consumers next quarter. The gap between a research prototype and a product on a store shelf involves billions of dollars, years of manufacturing refinement, and a whole industry of suppliers and fab partners who all have to catch up. That said, research prototypes like this are exactly how the industry maps its roadmap. When IBM showed off a 2-nanometer chip designed back in 2021, the industry took note, and the techniques from that work filtered into real products over the following years. This announcement is playing the same role. It's showing chipmakers and their partners what the next target looks like. The timing matters too. The demand for processing power right now is enormous. AI models are getting bigger. Data centers are consuming more power than ever. The pressure to do more computation per watt is intense, both for cost reasons and for environmental ones. A chip that doubles density while also improving efficiency isn't just a neat engineering achievement. It's directly relevant to some of the most pressing problems in the tech industry right now. For your laptop or phone, the downstream effects could be significant. Chips that do more with less power mean better battery life, cooler devices, and the ability to run more capable AI features locally without sending everything to a server. That's a real quality of life improvement, not just a spec sheet number. For data centers and AI training, denser and more efficient chips could mean running larger models for less money and less electricity. Given how much those costs have ballooned, that's a big deal for anyone building AI infrastructure. IBM is also not alone in this race. TSMC, Samsung, and Intel are all pushing in similar directions, each with their own approaches to 3D integration and new materials. The competition here is fierce, and that's actually good for the pace of progress. When multiple well-funded teams are racing toward the same general goal, the timeline tends to compress. What IBM has done with this prototype is show that Moore's Law isn't dead. It's just changing shape. The old method of simply shrinking transistors on a flat surface really is running into walls. But stacking layers, rethinking materials, redesigning the transistor geometry itself, those are new tools that can keep the curve going for another decade, maybe more. 100 billion transistors on a fingernail-sized chip. That's where we are in 2026. And if history is any guide, in a few years that number will sound modest compared to whatever comes next.